Okay, well, welcome to the start of the 2025-26 CEG seminar season. And our first speaker in the series is Yiping, who's been a postdoc here for the last 3 years and a day, or 3 years and a week, and a month. And this is going to summarize his work, his recent work on monitoring forests for carbon credits. And so it's off to Gothenburg in a few weeks from now for another postdoc. So this is sort of a farewell from him as well. So I had the pleasure of working with David and Yiping on this past projects on carbon credits, and so looking forward to the talk. So Yiping, all yours.
Yeah, thank you, Nisha, for the introduction. And so today, the talk I'm going to be talking about is how to make additionality credible again, or MACA quote. But more seriously, we're going to be looking at REDD+ projects, and so projects that prevent deforestation, and looking at how these projects, which could be a very important thing for helping dealing with climate and biodiversity crises, and two main challenges that they face, which is summarized here as how to evaluate their baseline and how to forecast their success. And so first, the context is that the reason why we need these projects is because all around the world, we have a rampant deforestation and forest degradation due to a number of different causes, such as conversion for commodity agriculture or timber extraction. And so you can see that in many areas around the world, it's happening at really alarming pace. For example, here you see it's the island of Borneo in Southeast Asia. Throughout several decades, you see where it's originally completely covered with forest, and now you have just a fraction of intact forests left. And when these forests are cleared, they release a lot of carbon, so they contribute a lot to carbon emissions around the world, and also they cause a lot of biodiversity loss. But the inverse can be true, meaning that if we stop and if we slow down this process or even completely stop it, we can actually reduce a lot of carbon emissions, and that can reduce biodiversity loss as well. So that would be a really meaningful contribution to the global crisis we're facing at the moment. And so this is where REDD+ comes in. It just stands for reducing emissions from deforestation and forest degradation, the plus meaning a lot of other things that people want to include. And so some analyses have estimated that the REDD+ projects denoted as avoided emissions here in this analysis. It has the potential of reducing carbon emissions up to 5 gigatons of CO2 per year. And if we compare it with some of the emission figures, the global total emissions is around 40 gigatons of carbon dioxide per year. And the emissions from transport is 8 gigatons per year. So if we actually harness all the potential of avoided emissions projects, it can be a significant contribution to reducing these carbon emissions. However, currently we're still at merely a fraction of this full potential. And there are a number of different reasons. And a lot of reasons is this analysis shows that due to a number of mobilization challenges, like challenges to attract funding or challenges to get people on the ground to actually implement the projects, etc., it means that at the moment, the supply of these emissions reduction can still be just a small fraction of its potential supply. And we're going to go into some of the challenges in a moment. But the one most mundane challenge is money. All these, if you want to set up a project, if you want to prevent forests from being cut down, you need to do something, and anything can cost a lot of money. And because unfortunately at the moment, globally public investment is still just sadly very insufficient. So there's been a lot of explorations into ways we can utilize private investment. And one key finance mechanism that can implicate the private sector is through what we call carbon credits. So for example, here is a patch of forest you want to save, you want to prevent from being lost. And you know, or you guess that if you do nothing, if you let business as usual to go on, a large fraction of it would be lost. But if you actually get people on the ground to agree to not cut down forests, to explore alternative revenues, or you prevent companies from coming in here and set up logging concessions, all these efforts, if they're successful, they might result in fewer forests being cut down. And so if we quantify the difference between these two scenarios, we get the emissions reductions that's directly attributable to the project interventions. And this can then be issued as carbon credits, which can be traded on the carbon market. There are buyers who want to buy it to simply contribute to global emissions reductions, or they might want to offset their own emissions, which is another controversial side, which we will not go into detail today. But the end goal is that by trading these carbon credits, people who buy these carbon credits, the money goes into project funding, and so this presents as an income source for the projects, for people to be able to continue carrying out their conservation efforts. And two small things we want to mention that is here. I mentioned comparing the two different scenarios, the business as usual, or what we call the baseline scenario, or what actually happens once you have the project. But this baseline is actually unobservable once you set up a project, because once you set it up, something has happened on that piece of land. You cannot see the same piece of land that didn't undergo anything. So this is technically an unobservable scenario, which is why a lot of people would refer to it as a counterfactual scenario. And also another term that you will often find in the literature is called additionality. This is just another term to call the emissions reductions, the actual emissions reduction that's due to the project interventions, because it's additional to what would have happened anyway if you hadn't done anything. So now that we have take this ideal scenario of how these conservation projects might get their money. There are still a lot of different challenges, but here we're going to talk about two main challenges. First one is we talk about the baselines, but we have to estimate that they're not observable. So how do we be sure they're accurate? And the second one is about how we can forecast the effectiveness of a project. And we will attempt to address these two challenges through two studies. And the first one is about how to evaluate the way we're estimating these baselines. So at the moment, there are a number of different ways to construct these baselines, and are used to issue actual credits that are being traded on the market around the world. But there's a debate between what kind of methods are good and what kind of methods are not suitable. And there's a main divide between what we call ex-ante and ex-post. So basically, the first kind of method, the most commonly used, is ex-ante methods, where we take something that has happened in the past and we project it forward into the future to predict or forecast what might happen in the future. And we use that as an estimate for the baseline. And the other method is called an ex-post approach, where you find places which can be used as a baseline, are comparable to the project, but you only observe what has happened in this baseline after a certain period. So you look back into the past and see what actually has happened in the baseline to quantify it. And so there's been some debate back and forth about which ones are more accurate. But the main problem is that we haven't had an objective and standardized evaluations that basically put them measure them in the same way. And so a lot of times we're just comparing apples to oranges. And when we are not sure which ones are really good and which ones are really accurate, there's a lack of confidence in how good these baselines are and how good the credits that are generated based on the baselines are. And this has been shown by some recent high-profile news reports that have cited studies that have demonstrated that in a lot of the methods currently used to generate credits, the actual emissions reduction is only a fraction of what they have been issuing as credits. So there's a big problem of over-crediting. Basically, the real benefit of projects are being inflated a lot. And so the ensuing controversy has really been quite detrimental to market confidence. And this has made it even more difficult for REDD+ projects to find the fund and to attract funding. And so so this shows that there's an urgent need to evaluate how we evaluate the methods we use to estimate baselines. And what we're proposing is to use what we call as placebo projects. So what are placebo projects? There are areas that are comparable to existing REDD+ projects, but where there isn't any actual REDD+ activities going on. And because of this characteristic, what we can make is an assumption called a parallel trends assumption. Basically, assumes that for these placebo projects, once we find their baseline, they should actually be the same. They should follow the same trend of deforestation and carbon loss. And so this concept has been developed and used in social sciences a lot to evaluate policy effectiveness. And it has also been used by some studies to evaluate the effectiveness of the REDD+ projects. So by when you evaluate one project to have certain amount of emissions reductions, you have to adjust it by what the same method would evaluate the placebos to have, so that you correct for these biases. And what we're proposing in this new study that was actually just freshly accepted last week is that we can use these placebo projects to not just to evaluate the projects, but also to evaluate the methods themselves by looking at how much bias they're generating, so that we can see how accurate and robust they are. And also another thing we looked at is whether these different methods to generate baselines, they perform differently when we use it on different periods in time. So just as an illustration, say here we have a project and we can estimate it, we can calculate its deforestation rate before this theoretical start project. And so we can generate different baselines. Some of the baselines we can use the past deforestation rate, either from within the project or from around the project. We can generate it in one way, or we can generate from the other. And for ex-ante forecast, we just take the past rate and we project it into the future. Whereas for the ex-post method, we first find the baseline that's matched to the project, and then after the project has started, 10 years after the project has started, we look at what has happened in this baseline, and then we calculate the ex-post baseline deforestation. And finally, now that we can also see what has happened in the project after this 10-year period, we can compare all these different estimates of the baseline against the actual deforestation, and we can see some of the baselines may be overestimating, and some may be underestimating. So this is how we can quantify how biased or how accurate these different baselines are. So to test these methods, we selected 27 placebo areas around the tropics that are comparable in size to existing REDD+ projects, but which are and with similar remoteness, accessibility, but without actual implementation of any REDD+ projects. So here's one example of a placebo project. They're all circular for simplification. And here on the base map, we have Landsat-based data product that shows annual land use change. So you can see from one year to another whether the pixels are like undisturbed forest in dark green, or there are other categories like degraded forest, deforested land, or forest regrowth, etc. And without going into too much into details, we were able to use these data sets to calculate over any period of time the deforestation rate that has occurred in an area by basically calculating the fraction of undisturbed forest that has been lost. And so now that we have this tool, we're going to look at how we can calculate and estimate baselines in different ways. So here we have a project. We have a project that we want to study. There might be some other projects that are separate in the vicinity, and we want to look at what happens in the project, but we're also looking to look at what happens in the surrounding region. So the way we do this is that we define a sufficiently large area around the project, but we also draw a 5 kilometer belt around every single project. And we do that because we want to exclude this part, because they're too close to any REDD+ projects, so they might be influenced by spillover effects. Maybe agriculture happening directly within the project might be just simply moved to right outside the project area. So we want to avoid that from influencing our analysis. So we will exclude these areas. And then we look at the countries the project are located in and the ecoregions that the project is located in. And by combining all these criteria, we define the surrounding region as the region that share the same countries or ecoregions as the project, but are outside of any project areas themselves or the exclusion zone. So after we have designated the surrounding region of a project, we can start to construct our baselines. And we tested 3 different ways to construct ex-ante baselines, which use data and information from before the project start to predict what might happen after it started. The first one is the simplest one, which is basically just looking at pixels within the project, and we quantify its deforestation rate. The second, and then we project that into the future as the baseline. The second one is called the regional method, where we use the pixels from within that surrounding region that we just defined, but which with environmental variables that fall within a certain range of the project pixels. So from that surrounding region, we find comparable pixels and calculate their deforestation rate and use that as the baseline. The third one is what we call the time-shifted method. This is a bit more complicated, but basically from that surrounding region, we're not only looking for pixels that fall within the range from the project pixels. We're actually looking for the one single best match. The pixel that's one single best match for every single project pixel, sample project pixel, but in an earlier period. So those pixels, their environmental characteristics in an earlier period will match the project pixels within the later period. And the assumption behind this is that when we do this, these timeshift pixels, they're kind of like a surrogate to the project pixels, but in an earlier period. And so what happens afterwards to the timeshift pixels in this period should be comparable to what happens to the project pixels in this period. So because these two are similar, these two should also be
clarification. I mean, you're showing the time shifted deforestation rate to be substantially lower than the project, but they will be matched, right, on the deforestation rate?
They would be matched. This is they could be they would be a match. I think this is just to this like not to scale, really just to read exactly
the z-axis. It's actually projecting out towards you.
Yeah. Yeah, exactly. So because these two are matched, so the assumption is that what happens afterward to them should also respectively be similar. So this part and this part should also be similar. And because this part is before the project actually starts, so we actually have this information. So we can use this information as a base, as a forecast of what might happen afterwards as a baseline. And so these are all forecasting methods. And we have another one, which is an ex-post method. So here we also do matching. We're also finding the perfect surrogates to the project pixels, but we're finding them in the same period. So here we have the matched baseline and also looking in the surrounding region. And so these two should be exactly the same. Well, should be very similar. And so what happens after that should also be similar. But because this part is after project start, so we can only get this information like a decade after the start, which is why this is an ex-post method.
Is your baseline pixels for ex-post, is that the same as number 2 in ex-ante or?
The regional one.
Yeah.
No, because for the regional pixels, we're basically saying like we look at their, let's say, slope, elevation, remoteness, and we have a kind of like a confidence interval of the pixels. All the pixels we will include if they fall within that range.
Okay.
But for the matching, for both the time shifted pixels and the match baseline, we're looking for every single pixel. We're looking at the one that is the absolute closest to this pixels in all the variables combined.
So we're doing one to
one matchings
versus one to many. Is that the main difference? Or?
Yeah, you can say that. But also we're not like it's not really a matching per se because we're including all the pixels that are similar, like just similar to a certain within a certain range.
Can I ask a question? With all of these, are you assuming that the ex-post methods, that the baseline is dynamic, right? Like the deforestation rate could change in those matched pixels through time. Whereas with the other ones, are you assuming deforestation rate is constant through time?
Yeah, exactly. So if we look at the 10-year, what we will compare is the 10-year average for the 10-year.
So just having one value for that.
Yeah, but if we look at another period, let's say 5-year, and then the forecast will still be the same, but then the ex-post, because we're now calculating the average within that 5-year, that could change. That could be different.
Yes, you're not actually plotting these through time. For each of them, you're just making one forecast, like one baseline deforestation rate value. You're not doing the annual deforestation rate, for example. It's just like this is the deforestation rate over a 10-year period. Over
a period. Yeah, we will actually look at what difference does it make when we look at different periods. So that here we're all looking at 10-year, basically like 10-year predictions. And so after we have all these different baseline estimates, we will compare it with what happens in the project in that decade after project start. And because remember that these are all placebo projects, and so nothing actually happens in these projects. So they should actually be reflecting in theory perfect baseline.
Right. So yeah. So these are not actual REDD projects. You're just evaluating the method. So no deforestation is happening here, and you're just trying to choose which choice of placebo choosing is the best one, or which choice of the control is the best control.
Yeah, I mean there would actually be deforestation happening, but like similar.
But you can't. This makes perfect sense. Yes.
Yeah. So this gives us a way to compare all the different baselines with something that is actually observable, as that can be a representation of the theoretically perfect baseline. And when we do that, what we found first is that the ex-post method is a lot better than all the ex-ante method that we tested by quite a big margin if we look at how well it fits the one-to-one line.
Wow.
And so another thing which, of course, doesn't mean that this ex-post method is perfect, because when we look at the bias, even though the ex-ante methods, they all show negative bias, which means that they're underestimating the actual baseline. For the ex-post method, we actually have a positive bias, which means that we're overestimating. So it could suggest that the way we do matching could still be improved, or maybe we should improve and add more points to improve, quantify the
question. I'm happy to wait to the end if we want to keep going. But I was wondering, is the reason the ex-ante methods are all negatively biased, so they're all overestimating the deforestation?
So it's underestimating. So yeah, so
the observed is higher than the
observed is higher
that
than
because is that just a general temporal trend that in general deforestation is increasing?
That is our main,
across all the projects.
Yeah, that is my main hypothesis of why this might be happening. And so this is for the 10-year period. And now the question now is that what would happen if we look at not just 10-year, but like periods of shorter time, the 9-year, 5-year, or 1 year? How would the baseline perform in this case? So here we're also just showing the bias and the goodness of fit of different methods. So with the bias, we see that all the ex-ante methods, the thinner lines, they kind of shift from having a positive bias when they're predicting shorter periods just after project start to a more negative bias for longer period start, except for this one, which is all negative bias and just getting worse over time. Whereas the ex-post method is kind of consistently having a low, but not really changing, slightly increasing, but not by much, positive bias over different period. And when we look at the goodness of fit, this is reassuring in that it really has a really high goodness of fit compared to all the others across all the periods we're looking at. Oh yeah, sorry, something I didn't explain very clearly is that the x-axis represents basic periods that starts in 2011 and ending in 2012, 2014, etc. So towards the end, you're just calculating a 1 year interval, and towards the right, you're calculating 10-year interval. And we see that the ex-post method has consistently really good goodness of fit. And when we look at the different ex-ante methods, there's something quite interesting, is that this teal line is the project method. It does relatively well in the beginning for shorter periods, whereas the regional method does not really well in the beginning. But then when you go on to the longer periods, it flips. The regional methods are better when you predict longer periods, and the project methods are a lot worse when you try to predict longer periods. So just to summarize, we've shown that this ex-post matching method does outperform all the 3 ex-ante methods that we tested. And this is quite striking finding, given that currently basically every crediting mechanism is using ex-ante methods. And although we're not saying that, because we're not testing those methods, we're testing our methods, even though those are the ones the best we could come up with. So even though this is not definitive proof that all the ex-post methods are better than all the ex-ante, it does give us confidence that we might want to push for exploration of more ex-post methods in the crediting mechanism. And also, with the thing I mentioned earlier about the project comparison between project method and the regional method and how their performance shifts through time. I won't explain too much here, but just if you can hold on to this thought as a cliffhanger for now, project better for shorter, region better for
I am
longer.
hanging and I was hoping there's like some way to like explain.
So, okay, so yeah, I guess I can
It's okay. It's
explain
okay.
there's a hypothesis, but there's also like a follow-up to this, which is why I want to hold on to this for a while. I guess the easiest, simplest hypothesis we have for now is that when we look at what happens in that placebo area, in the shorter term, it will really just resemble what is happening in its immediate, like within it. But over time, because deforestation pressure, they might come in from the surrounding regions. So what happens in the region what happens in the project might resemble more and more like what has been happening in the surrounding region.
So it's like basically feedback loops.
But that's because of the way the deforestation spreads. If the deforestation was to spread like you drive to the middle of the project and start from there, then you wouldn't see. But because of the spatial pattern that we're always going from human settlements from outside, we're coming in. That's why
probably
you're choosing a surrounding region.
Yeah, and I think there's a lot of interesting things we can test.
Like my assumption was that it would be something to do with just the size. That when you're doing the regional, you're looking at a much larger area, so the kind of shorter term trends are kind of averaged out, but the long term trend is more accurate. Whereas when you look at the project, it has the shorter term dynamics because it's in the right place, but that isn't representative of actually what might happen in the long term for that. You know, like it could head off in a
reversion to the mean.
And
Interesting. That was like the regional is enveloping
It's a
the
spatial
project. It's always got right. Because you were choosing the regional around it, so it also has a spatial component.
Yeah, it also has to do with the way we choose it. We look for certain areas with a certain like accessibility, remoteness range, similar to the REDD+ projects, which are usually like they would be set up a lot of times in an area that's not deforested yet, but there are immediate threats around it. So that's like the context of REDD+ projects in general. And I think our placebo selection will reflect that. And it might be worth exploring what happens if that changes. But but there is a follow-up to this point, and we'll talk about that later. And so, of course, we have a lot of things we can improve on from this study. We can always increase the number of placebos to have better and to have more confidence in our estimates. Then that would also allow us to test how the results might be sensitive to, for example, what data we use, what criteria we use to choose these placebos, and to do the matching. And it will also be worthwhile to quantify and propagate all uncertainties due to the data we're using, especially with remote sensing and other geospatial data. But importantly, I think this is something really interesting that can be operationalized into a standard benchmarking tool. For example, we can provide these placebos as a public available data set, and anyone with a current method, or if they come up with the method they think is better, they can just test their method on this set of placebos to see if it actually is better. And this could really help the development of new and better methods to be much faster. And also because we're testing how we can better estimate baseline. And these baselines, they're the foundation of not just REDD+ projects, but also other kind of nature credits, such as jurisdictional REDD+ projects, or even biodiversity credits. That means that this can be extended to other nature credits in principle as well.
Just to say, I mean, we can discuss this later, but this can be extended everywhere, because in every study, you need to choose a control. People are choosing controls without any quantifiable justification for it. So for example, when they look at post-fire recovery, they look at nearby unburned forest as a control. And I did similar, like was experimenting with similar things, and actually that does not make sense. For example, if you had a big fire, because things within that are very different from, so just matching based on distance, which is the most commonly used control choice in ecology, is often not suitable. So if you had a test, like a way for people to choose, how do you choose a control for any kind of comparison you're trying to do? And a methodology you can follow to test that robustly, what applies everywhere.
Yeah, I agree, because this is something that we kind of borrowed from social science. So they have been using this approach to test for policy, because for policy, they want to know how effective it is, and they need to have control. And so it is a very valid question for their field as well. So yeah, this is why there is this concept of placebo. Yeah. So take home message: placebos can help evaluate and improve baseline estimating methods for REDD+, which could enhance market trust and the viability of REDD+ projects. And current evidence suggests that ex-post matching methods outperform ex-ante forecasting. And also these placebo evaluation can be applied to other nature credits, and as Romana said, to other studies as well. And so now we kind of address the first challenge about how we can estimate baselines. But there's the second challenge, which is how well we can forecast the effectiveness of the project before it even starts. And the reason this is important is that the funding mechanism I talked about, carbon credits, even if we have a perfect baseline, they're usually issued way after the project has already started. And this is because no matter what baseline we pick, we will have to observe what happened to the project after it's started, after it's already been running for maybe 5 years or 10 years, before we can calculate the actual emissions reductions. And only by then, carbon credits will start to be issued, and then money might come in later because their administration and all that. But during all this time, the project developers and local people, they still need money to survive and to make sure that the project is working, is running. And also, more importantly, even before the project starts, before any of that all that happens, you need a lot of upfront investment to get things going. You need people and the government to be on board. You need to train personnel. You maybe need to develop policies. All of that takes time and money. So it means that we need a way to kind of demonstrate the viability or the potential of the project before it starts, so that there's a better chance for people to attract some form of upfront investment. So this is why we still need a forecast, even though we show that it's maybe not best for getting baseline, but it's good for other things. And so there are some newly developed methods that do provide forecasts of carbon deforestation or carbon loss in a more systematic way, but there are still issues with them. So like, for example, there's the most recent VN40A. We don't need to talk about details, that kind of generates a map of deforestation risk. And this is a lot better than what we had earlier. But one issue is that we're still choosing kind of an arbitrary period in the past to forecast an arbitrary period in the future. Like for VN40A, they're using the 10-year historical data to predict 6 years after the project starts. But why 10 and 6? Would it be a better forecast if we choose a different number? No one really knows yet, because we haven't systematically tested this question. And then the other issue is that what we have been talking about is how we can forecast baseline. And this is relatively simple, because baseline, they're just what things have been going on if you don't do anything. So you can forecast their trends. But when we want to forecast and predict emissions reductions, there's the difference between what happens in the project and what happens in the baseline. And what happens in the project is a lot more variable, because by definition, you will have implemented different policies or different activities, and they may be effective or not. They may take time, and it's a lot messier. So project carbon loss and by consequence, the emissions reduction, they may be influenced by a lot more factors. Maybe maybe the environmental characteristics of the project or the economic activities of the country it's in. So we still don't know what factors really affect these. So just to illustrate, we have project and we have what happens in the project and we have what happens in the baseline. When we're doing the forecast of the baseline carbon loss, the first question is, we can take any of these historical periods to forecast any of these target period. So which one would be the best? Which one would be the most reliable? And the second question is, the project carbon loss might be variable depending on how effective the interventions are. So what can be used to predict project carbon loss? And finally, by consequence, the emissions reductions are the difference between the two. So what factors can be used to predict emissions reductions? So here, this is a manuscript still. This is a study with nearly finished, just preparing the manuscript. Hopefully you can submit it pretty soon, maybe to carbon balancing management. But if there's any recommendations of other target journals, we're very welcome to suggestions. So the aim of this study would be to address those three questions. First, to see how the performance of forecasts of baseline carbon loss can vary different depending on which periods we're choosing to generate forecasts and which period we're forecasting it on. And the second is to identify what social, economic, and environmental variables can help predict project carbon loss. And finally, we also want to look at what variables could predict emissions reductions. So to do this, we look at 27 ongoing REDD+ projects across the tropics. So these are real ongoing REDD+ projects of different size in different contexts. And also now we're looking at actual carbon loss rate. So again, not going into the details, but we combine data, Landsat-based data that tracks annual land use change, plus the biomass estimates based on the spaceborne LiDAR JEDI, and we combine those to allow us to estimate annual carbon loss rate over any given period of time in any given area. And so just a quick reminder that for any project, we will have found the surrounding region of the project in the same way as before. And so from that, we can generate forecasts from three different ways. The first one is we take the carbon loss rates in the project area. So again, we can calculate it for various different historical periods from 1 year, 3 year, 5 year, or even 10 year. And then we can use that as a forecast. This is what we call a project-based forecast. And similarly, we can use the carbon loss rate in the surrounding region. Again, we find the comparable pixels within the surrounding regions. And then we use those as region-based forecast. And then finally, the thing I asked you to hold on to, the cliffhanger of project better for shorter, region better for longer. That's something we found for deforestation rate in the previous study, but here we posited that it might work similarly for carbon loss as well. So what we did is to invent what we call a mixed forecast. That is a mixture of the project rate and region rate. So that this time it's time variable. For the project and region-based forecast, it's the same number, no matter which target period we're looking at. But for the mixed forecast, if it's a shorter target period, then because we're using a weighted geometric means, it will be closer to the project rate. But if it's a longer target period we're looking at, it will be closer to the region rate. This part might be a little bit confusing, so.
Would you mind explaining that again, sorry? Yeah, could you just explain that again? Like why the what you mean by why when it's longer it's closer to regional? Like
so we calculate the weighted geometric mean. So basically, for example, here for the first year, for the 1 year target period, we'll kind of like 9 parts of the project rate times 1 region rate, and then we did the geometric mean. And when it's a 5-year target period with a five parts project rate, 5 part region rate, and then we calculate the geometric mean so that it will be.
Because you're already expecting, so you're hypothesizing that the region-based forecast is going to be better in the long term, the project one is better in the short term. So you're constructing your weighted mean based on that assumption.
Yeah, based on that assumption. Yeah. So this is what we observe for deforestation rate. With carbon loss rate, there might be more variability, but here we're making an assumption that this might still hold to a certain extent. And so after we have these different kinds of forecasts, we also have the observed baseline, because these are projects that's ongoing for maybe 5 years, or a lot of them are over 10 years. So we can calculate what has happened in the baseline. And again, we will compare the baseline with the forecast and see how well they fit together. And to do that, what we do is we fit a linear model, so using the forecast to predict the observed, and then we calculate the performance statistics. We don't need to go into details, but just goodness of fit, error, and bias. And then what we want to do for the following steps is that we actually do want to pick one that is the best according to our results. So for that, we specifically look at the 5-year and 10-year target periods. And we do that because this is the most common predicting periods in the current methodology that exists. Most people are issuing credits at the 5-year or 10-year interval. And so for these periods, we look at how good the different methods are, and we rank them, and then we basically look at the one with the highest rank. So the result shows that. So here we have 3 different types of forecasts. The green is the project-based forecast, the regional-based forecast is in brown, and the purple one is the mixed forecast. And we have them to predict target periods of 1 year, 2 year, all the way to 10 years. And what we see is that the purple one is consistently on top in terms of goodness of fit. It's got the highest goodness of fit. And also when we look at the bias, it's got the lowest bias as well, except for the longest periods where all different types of forecasts seem to converge, becomes very similar. And also we see that overall for longer target periods, there's a better forecasting performance. We have higher goodness of fit and lower bias. Again, except for the longest periods where it kind of seems to stabilize.
This doesn't, am I correct that this hasn't replicated your previous result of the fact that the project-based baseline, the project-based ex-ante baselines are better than in the short term and regional better in the long term, whereas here the project is always better than the regional?
Yeah, so I think the main reason there's this difference is that here we're fitting a linear model from forecast to baseline, and whereas before we're simply looking in the previous study we're simply looking at how much they deviate the one-to-one line. But here we're saying that we want to empirically we fit the best linear model, so that even if it's not on the one-to-one line, if it's well clustered on another line, and we fit a model that can explain that variation really well, then it would still be a good forecast. The performance statistics will still be high.
But you could try here and test many different kinds of models. Like instead of just the linear forecasting, or you could try like different from previous historical project information, you do some prediction with that, and then.
Do you mean that adding like other environmental variables even here?
Well, just like a different model is not like you could put in the machine learning like previous temporal sequence of the project pixels and have it predict 10-year.
Yeah.
And then evaluate like how much it matches what actually, I guess, happened, and how good of a it's like a test bed for evaluating many different kinds of models.
Are you saying the linear model was used for the forecast, or was used for assessing them, the performance of the? Sorry, are we saying the linear model was used for actually doing the forecast, or the linear model was used for assessing like how close the points, the observers to the forecast? I wasn't sure which one you were saying.
It's just for I guess it's to assess how well they're correlated, because we fit a
Okay, so
once we fit the linear model to it, and then
the actual way you're doing the forecast is still the same as before, where it's just assuming the rate is the same.
yeah.
Okay.
Yeah.
So
Yeah, at least for the
linear model is actually used for the
Yeah.
forecast.
I see.
at least for the project and for the
I see.
region.
Okay.
Yeah.
Hmm.
Yeah, so we see that overall the mixed forecast is performing better, and the longer target periods are better forecasted.
Still, the R square is
Also there.
fairly small, right? We're talking about,
Yeah, it's a lot smaller than before.
yeah, and also I'm surprised to see that the goodness of it increases over time. You should be declining. You should be forecasting better at the start and getting worse as you go forwards in time. You see what I mean?
Yeah,
Sort of weird that it's doing badly in the beginning and getting
Yeah, why
better
is it
worse.
doing,
That's
why is
the
it doing
opposite.
badly in the beginning?
Is it because these are cumulative rather than predicting what the loss is in a year and 5 years time? It's between now and 5 years. If you're doing a forecast, the window is longer, so therefore you're going to have a reversion to the mean as well, where the variability will be much lower than
Oh,
short-term
Mhm.
forecast. What it happens next year could be really high, really low, because deforestation is like all over the place.
Mhm.
Yeah,
If
that's-
we're predicting a 5-year
Oh,
window,
there's like a lot of
It's
intra-annual.
averaging out.
It's averaging
yeah, that's my interpretation as
I
well. Is that
see.
for the shorter periods, there's a lot more
Mhm,
like
like year to
stochasticity
year is very hard to
that's
predict.
actually more averaged out over a longer period.
That makes sense.
Interesting. Okay.
Yeah.
But am I wrong to assume that you could potentially try different ways of, like, different forecasting models?
Mm.
Is like, am I understanding, you could, because you're trying to like predict, give a
Yeah.
future prediction based on historical projects, like 10 years of project data. You could feed it
You
into
could
something.
focus
Yeah,
anything
yeah.
you want.
And that,
Yeah,
yeah, but I'm saying like,
Yeah.
the way you set this up is nice because you could just try a bunch of different forecasting models.
Yeah,
And see
Yeah.
which one performs better.
Yeah.
And then that's your winner, but you
Yeah.
have a way to now rank them,
Yeah.
I guess.
Yeah, I think
Yeah.
the what you're saying is true. I think the problem that we run into, is that actually evaluating the forecast is very computationally expensive,
Mhm.
right? Because you're kind of okay, maybe the forecast is easy, but right, actually making the forecast is easy.
The
but
matching is
but
competition,
Yeah.
but once you have the matches.
Yeah.
yeah,
you have.
once I have
Now
that,
you can
yeah,
try out
yeah.
a bunch of
Yeah,
different.
because
the matching is what provides the forecast. The forecast is just based on observing what happens in the match pixels.
But you match them based on the prior 10 years.
Yeah.
And so
After that, you
now
can do
you're
whatever
done.
you want. You could throw darts and do a forecast based on throwing darts.
Yeah,
Which is what
like-
the experts do. I mean, that's
Yeah, because you
Yeah,
just.
like the mixed forecast, I do it this way. I could do it in this way or this way. Well,
Or
no,
again,
it's-
you could just
I
feed the
can- yeah, it can
historical
be- It
period
can be skewed towards project rate
somewhere.
or skewed towards region rate, or it can be mixed, but also.
Yeah.
temporarily
You're the ones
constant.
in neutral
Yeah,
network, actually.
I don't actually, but I think like this is nice because once you've done the matching and you provide, as you kind of said, like you
Mhm.
give people, these are the matched things, and now you can just. You can like put in a different model and
Yeah.
people, it could be a competition on the
Yeah, Kaggle.
Kaggle, yeah, like we developed the best REDD plus forecasting model.
Yeah,
We matched projects, this is the criteria for evaluation, you can directly measure.
of course, there will be a problem. Here, there will be a problem of overfitting. Like if you could find the best one for these projects, and then.
That's it.
Well,
have
you
a whole
reserve-
set,
You
yeah.
reserve 7 of the 27, you
Mm.
reserve 7,
Yeah.
that's your test, you don't give them
Yeah.
that, just at the final.
Yeah, yeah,
I think that's a very good idea.
yeah. So I think we're running low on time. So long story short, we did find the best forecast for like best out of all of those for the 5 and 10-year prediction. And this is how they look. It's 6 to 6.5, 0.665 goodness of fit. But the error and bias on that big. So that's kind of reassuring. And then now we have the best forecast. We want to add more variables to predict what happens in the project loss rate, and then also predict the emissions reductions. And so here it's a more traditional linear model. with included a bunch of predictor variables, like with the forecast, initial carbon density in that area, slope, remoteness, the size of the project, and data from the World Bank, like GDP and corruption index, because who knows that might affect. And then we selected the best model using model selection with AIC. So it's pretty classic. So this is for the project carbon loss. Like overall, the fit is still, it's kind of similar at a similar level. Although this one does have a much larger error, I'm guessing it's because of this more outlying point that increases the error. And so we see that there's the old ones are the significant effect. The forecast of baseline carbon loss does also help in predicting project carbon loss a lot. But especially for the longer period, for the 10-year production, we also have a larger size means larger project carbon loss, and higher GDP growth rate means higher project carbon loss, but more remote projects will have lower project carbon loss. So this intuitively they make sense. And then what's more troubling is that when we predict the emissions, actual emissions reductions, even the goodness of it is similar, but now it is worse for the 10-year prediction. And even after model selection, we see that actually it's not significantly related to any of the predictor variables, whereas we do see some significant effects for the shorter prediction, even though some of them have really small effect size. And the largest most influential predictor is actually initial carbon stock. Like if we have higher initial carbon stock, then there's no emissions reduction.
Oh, what happened there? Sure.
What happened is actually my battery is my battery is ridiculous now. At 1 hour will make it dead. But that was actually the last slide of the results. So that's
It's a wonderful way to end this.
literally my problem.
That we stop the recording here. Okay.
Yeah, I can just